In this video, I'm going to explain a very different way of using Hopfields' energy function. We add some hidden units to the network, and what we try and do is make the states of those hidden units represent an interpretation of the perceptual input that's shown on the visible units. So the idea is that the weights between units represent constraints on good interpretations, and by finding a low energy state, we find a good interpretation of the input data. Hopfields Nets combine two ideas. The idea that you can find a local energy minimum by using a network of symmetrically connected binary threshold units, and the idea that these local energy minima might correspond to memories. There's a different way of using the ability to find local minima. Instead of using the net to store memories, we can use it to construct interpretations of the sensory input. So the idea is that we have the input represented by some visible units, and we construct an interpretation of that input in the set of hidden units. So the interpretation or explanation of the input is going to be a binary configuration over the hidden units. The energy of the whole system will represent the badness of that interpretation. So to get good interpretations according to our current model of the world, which is in the energy function, we need to find low energy states of the hidden units, given the input represented by the visible units. I want to give an example of this to make the idea clearer. In order to give the example, I need to go into a little bit of detail about what you can infer when you see a 2D line in an image. What does that tell you about the three-dimensional world? So a 2D line in an image could have been caused by many different three-dimensional edges in the world. If this blue dot is your eyeball, and the red lines are two lines of sight coming from the centre of your eyeball, then the black line is a possible 3D edge that would lead to a two-dimensional line on your retina. Here's another 3D edge that would lead to exactly the same thing on your retina. And here's another one, and here's another one. All of these different 3D edges have exactly the same appearance in the image. That's because we've lost the information about how far away the ends of the line are along that line of sight. We know the end is somewhere along the line of sight, but we don't know the depth. So if we assume that a straight 3D edge in the world is the cause of a straight 2D line in the image, then we've lost 2 degrees of freedom of that 3D edge, its depth at each end. So there's a whole family of 3D edges that all correspond to the same 2D line. You can only see one of these 3D edges at a time because they all get in the way of each other. So now we're in a position to see a little example of what you might be able to do if you can use the fact that you can find low energy states of a network of binary units to help you find interpretations of sensory input. So here's the example. We imagine we see a line drawing and we want to interpret it as a three-dimensional thing. So the data we have, let's suppose, is a bunch of 2D lines, like the lines shown in the picture. And for each possible line, we will have set aside a neuron. Don't worry for now about the fact that that would require too many neurons. So for every possible 2D line, we have a neuron. In any one picture, only a few of the possible lines will be present, and so we'll activate just a few of those neurons. So I've shown 2 edges in that picture, activating 2 of the neurons. And those are neurons that represent 2D lines. They're the data. Now, what we're going to do is have a whole bunch of 3D line units, one for each possible 3D line or 3D edge. So each of the 2D line units could be the projection of many different possible 3D lines. We therefore need to make the 2D line unit excite all those 3D lines but we also need to make them all compete with one another, because you can only see one of them at a time. So here's an example where I have a stack of 3D line units. The green connections are excitatory connections coming from the 2D line unit, all of them with equal weights, saying if this line unit is present, I'm going to try and turn on all of those. But in addition, we need competition between those so that only one of them will turn on, and that's what the red lines represent. And we do that for each 2D line unit. So I'm just showing it to you for the 2D line units that happen to be active at present. And again, don't worry about the fact that this would need far too many units. Now the story is not quite complete. We've now wired into the neural network the information about projection that I showed on the previous slide, i.e. the neural network in those green and red connections understands that each 2D line can correspond to many different 3D edges, but only one of them should be present at a time. But now we know a lot about how 3D edges connect. For example, when we see two 2D lines connect in the image, we think it's almost certain they correspond to edges that have the same depth at the point where the lines connect. So let's suppose that the two 3D edges I've joined there correspond to having the same depth at the point where the two 2D lines join. That means they should support each other. It doesn't have to be like that. You could have a very funny viewpoint where one line ends at a different depth from the other, and you just happen to be at the viewpoint from which they coincide on your retina. But that's very unlikely. So we're going to need to use the fact that we expect 2D lines that coincide in the image to correspond to 3D edges that agree on the depth at that point. So we'll put in a lot of connections like that. But there's an even stronger fact we can use, which is that in our manufactured world, we expect that quite often 3D edges will join in a right angle. And so for two particular 3D edges that happen to agree in depth and join at a right angle, we'll put in a particularly strong connection. And I've indicated that by a thicker green line. So by putting in lots of connections like that, we can indicate how we expect 3D edges to go together to form a coherent 3D object. And now we have a network that contains information about how edges go together in the world and about how edges project to cause lines in the image. And so if we give that network an image, it should be able to come up with an interpretation of the image. And for the image I'm showing you, there's two quite different interpretations. It's called a Necker cube, and if you look at it long enough, it will flip in depth on you. And this network would have two pretty much equally deep energy minima that correspond to those two interpretations of the Necker cube. Remember, this is all just an analogy so you understand the idea of using low energy states as interpretations of perceptual data. To actually build a proper model of what happens when the Necker cube flips would be a lot more complicated than this. So, if we decide we're going to use low energy states to represent good perceptual interpretations, then we have two issues. The first is to do with search, and I'm going to deal with that in the next video. The search question is, how do we avoid the hidden units getting trapped in poor local minima of the energy function? The poor minima represent interpretations that are suboptimal given our current model in the weights of the network. Can we do anything better than simply going downhill in energy from some random starting state? The second issue, which seems even more difficult, is how do we learn the weights on the connections between hidden units and between visible units and hidden units? Is there some simple learning algorithm for adjusting all those weights so that we get sensible perceptual interpretations? And notice here we haven't got a supervisor anywhere. We're just showing it input, and we'd like it to construct patterns of activity in the hidden units that represent sensible interpretations. This seems like a rather tall order.